So thank you all for coming to this talk today. I'm pleased to introduce to you Dietmar Tourbier, who is the new director of Astri, the Australian Solar Thermal Research Initiative. And now might be a good time to remind everybody to turn off their mobile phones.
Please remember to turn off your phones. This was actually my boss calling, and I'm not going to answer it.
I will let Dietmar make his own introductions. He's been with Astri now for 2 months and comes from a background with GE.
Yeah, thank you very much, Renate. So welcome to today's talk on solar thermal, and I'm pleased to be invited. And to be quite honest, this is my first public talk about solar thermal. So you're an experiment. Let's look at it that way. And as Renate said, my name is Dietmar Tourbier. I'm new to Australia, and I'm also new to Astri. I'm originally from Germany. Spent 18 years in the United States getting my PhD in aerospace engineering, out of all things. Before I did that, I was a student in a high school in Germany, and in 1982, that was grade 11, so it tells you how old I am, I was working on something called a solar cell, and most people that I talked to didn't know what it was, and I was intrigued by it. So I was testing the efficiency of a solar cell, and I was amazed to get a whopping 11% efficiency out of it. And I did a costing estimate for a house heated by solar cells, electricity, and realized the payback time was, I think, in the order of 50 to 100 years. So back then, people told me, just forget about this whole solar thing, it's never going to work. That's a long time ago. And I think all of you are working somewhere in solar, I'm guessing, right? So that should be music to your ears. At the time, this is 1982 is 35 years ago. So at the time, it was quite a different picture. So I actually decided to do something different, go into aerospace engineering, because that was very interesting. So I went to the United States, got my PhD in aerospace, and then started working for a company called Honeywell, which I think you know, and then was acquired by GE. At the time, I was working on fuel cells, because fuel cells in the 90s and in the early 2000s was an oncoming technology that a lot of companies invested a lot of money in, including GE. So I was working on PEM fuel cells, that is low temperature fuel cells, and also solid oxide fuel cells, to see if it can have a role in the energy mix for the United States. And GE decided in 2006 to stop working on fuel cells, not because it doesn't work. Because the reason was that the commercial viability for large power generation was just not there for fuel cells at the time. And I think still today we're struggling with that on fuel cells. So at that time I decided to move back to Europe, and I was leading the corporate research center for GE in Europe over the last few years. I built a power electronics team. I built a team on electrical technology, machines, meaning generators, motors for renewable energy. So I still stayed with renewable energy at the time. That was wind energy and solar energy. And that was roughly the time when solar, PV solar, started really coming down in cost. So that became quite intriguing to me. And living in Germany and having been from Germany, solar at that time was really a key thing to do. So I was in Germany, and I have on my first slide an interesting map that I'm sure you all have seen. So this little circle up there on the top, that's Germany. That's nice and green. Green means it doesn't have much sun. Yet, for many years, Germany was the prime country for solar development, solar installation, because the people and the country believe in solar as being one of the solutions for the energy mix in the future. And but it wasn't until the rest of the world came into solar as well, until volumes came up and drove the price down, that it really kept getting some traction, or getting a lot of traction. And so recently, I decided for personal reason to move to Australia. So I looked at Australia in terms of solar, and I was like, wait a minute, look at that nice red spot in Australia. So Australia has a lot of sun. The first time I came to Australia was in 2006. And I was shocked, to be honest. I was shocked to see and hear that nobody was using solar. And I came from a country like Germany. When you fly over Germany with an airplane, you see PV panels almost on every roof. And that was already 10 years ago. That's not something that is only new now. In fact, 5 years ago in Bavaria it happened to be the first day in Bavaria that solar PV created more energy for an entire day than the state needed. That happened 5 years ago already, so it's not new to something like Germany. So I came from Germany to Australia, and as I was flying in over Melbourne, I was looking for solar panels, and I saw none, not a single one. And that was shocking to me. It's like, why is there no solar in Australia? And there can be many reasons. There is a lot of other things in the energy mix in Australia that can be used as an argument why there is no solar, but it's certainly not a technology argument or an argument there's not enough sun in Australia. And I was very pleased recently to see that things have changed quite a bit in Australia. Okay, so Australia certainly has, out of all places, if you look at the entire continent, the best situation for using solar irradiation for energy generation. And I know you all know this. This is not new to you. When you look at it more closely, there is Germany on the left, and there's Australia on the right. The interesting thing to see here is what I mentioned earlier. The predominant solar power generation in Germany, as you may or may not know, is in the south. There's hardly any solar generation in the north. What do we have in the north? Wind. So there's a lot of wind power in the north of Germany, and there's a lot of solar power in the south of Germany. The wind situation in Germany, I didn't put up a wind map, but the wind situation in Germany in the south is not very good for wind being a predominant power generation, but solar is. As far as Germany is concerned. Now, when you look at Australia, one thing that wasn't apparent to me initially, but when I looked at it in a second time, I realized it's nice and red in the center, but where do most people live? On the outskirts, where it's not big red, right? So it's not really that obvious that you have that much irradiation in Australia to readily use where people live. So it's a little bit away from that. When you think of where do you have the irradiation and where do you need it. So you also need to make sure that you have plants in the area where you can have enough sun and where you can provide it to the people where they live. Okay, so that's the situation that I came in. And then I asked myself, comparing these two countries, how does Germany compare with Australia in terms of renewables in the energy mix? And so I found this on the web recently. But this wasn't new to me because I've been looking at this for the last few years. And when you look at Germany over the last 10 years, so you see a nice growth in energy mix. Predominantly it's wind because it's in the northern part of the country. But you see that PV, solar, that's the orange curve, in about 2010 has really started ramping up. And that was predominantly driven by economics because PV became a lot cheaper. Also, Germany at that time had a very large feed-in tariff. I don't know if you're familiar with that. It was about 41 euro cents per kilowatt hour compared to I think an average cost of electricity for a resident was about 23 cents. So you could actually make money with this. And people did. So there was a lot of solar installation. And once that started taking off, Germany started tapering off the feed-in tariff. Today, I don't know exactly what it is anymore, but it's almost at grid parity, the feed-in tariff, which is still better than most states in Australia. In terms of what you can get for it. So the payback time for a solar residential installation today is in the order of 5 to 6 years, even today with the feed-in tariffs you get today. And it was similar back then. PV was more expensive, but the feed-in tariff was higher. So the payback period has roughly been stable about 5 to 6 years in Germany without storage. So this is all talking without storage. Now look at Australia for that, and I'm pretty sure that most of you are familiar with this as well. It looks like there is an incline. It's not really that strong though. The most incline you see here is wind. Over the last 7 years, 6, 7 years, wind has seen an incline there. But when you look at PV solar, that's the little blue curve. I don't know if you can actually see it. It's right here. So one of the things I realized when I came to Australia and I talked to people, they said, we have 10% of solar already in America. I said, well, are you talking about capacity or are you talking about energy? And when we talk about how much renewable is used, I always like to talk about the energy that's used over the whole year. And that is still a very small amount on PV solar. This is only the small scale. No, this is the large scale. Sorry, I mixed it up. The small scale one is already higher. It's 2 to 3%. So it is coming up. It's still a small part of it. But I think what we will see, if you extrapolate this in the future, you'll see that that is actually going to grow. What is interesting, though, is what's the reason for this to grow? Is it because people want to have cleaner energy? No, it's not. The main reason these things grow is the same reason why it started growing in Germany. It's economics. And if you look across the world, today already, PV and wind are, in most places in the world, the cheapest power generation that you can get compared to fossil fuels and compared even to nuclear, if you include the building of new nuclear plant and the dismantling of nuclear plants in the cost of electricity for a nuclear plant. So we as a community have reached a point where renewables clearly can be, and already is in a lot of places, the cheapest way to create or to generate electricity. Okay? So that is very good. And we will see from driving it on economics that that will help the uptake of it in the market. Okay? So far I don't think I've told you anything new. Oh, before I go there, one of the reasons I was told in Australia why there is so much, why the take on renewables is so much lower than Germany is because there's a lot of coal in Australia. So there's still a lot of production of electricity from coal-fired power plants. And that is one of the reasons that's holding renewables back. So I actually went and looked at what has Germany been doing and look at the part of power generation in Germany that's coming from coal. It's not all that different from Australia. So Germany has a lot of coal as well. It's more expensive than Australia, I understand that. But regardless of having coal available in Germany and having a lot of coal in the energy mix, that hasn't stopped renewables from taking off. And it shouldn't stop us in Australia either. So I'm not a preacher that says, let's stop all the coal-fired power plant and let's make all renewables, because I think that would be the wrong thing. There's a transition period. Coal-fired power plants in Australia will come offline because they're aging. And what's going to happen when coal-fired power plants come offline, they have to be replaced with something. So either we're going to build more coal-fired power plants, and in some cases probably we will, and probably we should. But I think I'm a firm believer in having a right energy mix rather than having one solution that does it all. I know that not everybody agrees with that, but I've seen this at GE for many, many years. If you believe in a portfolio, we should drive the portfolio in the right direction. So what you can see here, this is for Germany over the last 15 years, is in Germany we're fading out the fossil fuel, and as you project that into the future, it'll probably become less and less and less. One reason is fossil fuel is going to become more expensive, and we're going to run out eventually. I don't know when. There are all these different forecasts that you can see, but we all agree eventually it'll happen. We will run out of fossil fuel, and we have to have a solution at the end that provides energy to us, either from nuclear. Maybe we'll solve the problem with fusion. I don't know what's going to happen, but I don't think in my lifetime we'll solve that problem. So renewables is certainly a great way to get there. But I also firmly believe that it will not be one kind of renewable that does it all. I don't think we'll move to 100% PV or 100% wind or 100% solar thermal. Okay? So the question is, from all this, how are we going to get there? So when you look at renewable costs and the different types of renewables over the past, I think this was 7 years, and you see the curve of cost coming down for biomass, geothermal, hydro, PV, solar thermal, offshore and onshore. The two steepest curves that I'm actually seeing here coming down is photovoltaic, and it also is solar thermal. Okay? So solar thermal is today more expensive than PV. But I think that eventually it'll come into a range where it makes sense for it also to be part of the mix. So I'm coming back to the story I said earlier. When we think of a solution that will work, I'm a firm believer that the solution will be a mix of technologies. Which one of them will be the winner will be driven by economics. Okay? So how did this happen? What has been driving these cost trends, specifically the one in PV, is largely due, in my opinion, to volume. Okay? So when you look at the number of installation, that's across the axis here in megawatt, over the different years, and you see the cost curve coming down, it's a clear correlation between the amount of volume that has been produced and the cost. Now you can always argue the chicken and egg problem. Is the volume driving the cost, or is the cost driving the volume? In the end, it's actually both a little bit. But without the volume, you're not going to get the cost down. So one of the things when you look at PV on the far right here is beautiful. It's a large volume that you get here. When you look at CSP, the solar thermal part, That's on the left side, so the volume is still quite low. What was interesting to me when I looked at this curve is that they're almost parallel, which was quite interesting. So if you extrapolate that, and careful, I'm not a big friend of extrapolation, you could say that, oh, we're going to come down here. Well, careful, I'm not going to believe in a linear extrapolation there. Yeah?
Isn't some of the solar thermal's cost reduction just by locating the plants in better DNI resource locations?
Yes, that is true. That is also part of it, is finding locations where you have a lot more DNI. Because it used to be that, and that's the same for PV. PV used to be available mostly in areas like Germany, like in Europe, like in Northern America. Now that we're starting to install it in Africa, we started to install it in Saudi Arabia, for example, in places where you have more irradiation, that's also driving the cost down. So it's a part of it as well, yeah. But it's largely, what I've seen at GE for PV was, we had a PV plant that we built, and we eventually sold PV technology to First Solar, which is publicly known. And one of the reasons was that we could not compete with the production cost in China, for example. When China came in on PV and they drove the volume up a lot, that drove the cost down as well. It wasn't only the cheap labor cost in China, but it also the volume went up so much that was really helping getting that cost further down. I'm seeing that now in solar thermal. Recently, there has been a lot of push in China to also get solar thermal online. And volume gets you learning, but volume also gets you companies entering the market and that compete with each other. That'll drive the cost down just through competition. And so we'll see the same in solar thermal as well. Where's it going to go? I don't know. If I knew that, I probably wouldn't be standing here. I'd be very rich somewhere and make a lot of money because I can do very good forecasting. But what I do know is that we're not done. These curves don't look like they're leveling off. So PV in some cases is already in the 2 to 3 cents per kilowatt hour, which is not on this curve, at least, and that's in the contracted cost for electricity. Some of these plants for solar thermal hit the 7, 8 cents per kilowatt hour as well. Now this is with storage. So I think this is a little bit lopsided to compare this because PV is without storage. Solar thermal is typically with storage. So if you compare solar thermal with PV, you should really compare solar thermal with some type of storage compared to PV plus storage as well. And then they're actually quite comparable when you look at that. Okay, so what I was trying to tell with this slide is what we need to do for solar thermal to also become more successful is to drive volume. But how do we drive volume? It's, again, the chicken and egg problem. How do you drive volume if you don't have the cost? How do you drive cost if you don't have the volume? So we need to develop some technologies that are better than what you can get today to help that drive. So having said that, I have 2 curves here. They're just, don't look at the cost per kilowatt hours. That was just as an example. And when you look at a standard learning curve or cost curve that is driven by volume, you have this exponential decay coming down. What is needed to get away from that is you need a step function to drive it down further. And that's where research comes in. So having research done, like you guys are doing on PV, and other universities are also doing on solar thermal, is can you find technologies that help you get a step function in lowering that cost? And this is just to illustrate that here. If you want to get away from that learning curve in a step function, you need to find different solutions rather than just driving the ones that you have today and expanding the volume. So how do you do that? Well, for solar thermal, what is a solar thermal plant today? If you look at most solar thermal plants that are out there, they are either a parabolic trough, where you have a parabolic line of mirrors that have a pipe with some liquid running through the focal point of the mirrors. And that liquid is heated up. Most of the time it's water. And you heat it up, you create steam, and you run steam through a turbine. The turbine drives a generator, and you feed that to the grid. So you have synchronous generation, typically. Or you have a tower where you have heliostats around the tower that are focusing on the center of the tower and heating up a vessel that has water in it. And then you use that to create steam in that vessel, and you drive a turbine, and you have a standard steam cycle and create electricity from that. So that's what a solar thermal plant looks like today. And then you can have storage in there that you either have with having water tanks where you can store the hot water, or you can have Some plants have concrete that they heat up, so you can store the heat in that concrete. So it's typically latent heat that you store. So when you extrapolate the capability of this process, you see that first curve that I showed there. That's the red curve right here, where you end up at a cost point that may or may not be good enough. So if you want to step away from that, you need to get more energy out of the same sun that you're collecting. How do you do that? So one way to do that, and we're not the only ones at Astri that have been doing this, a lot of places in the world have been looking at this as well. One way to do this is get a more efficient power cycle that you do. So you go to higher temperatures. There are a lot of issues that come with it, a lot of challenges that need to be resolved. But on paper, when you look at a higher temperature CSP, the higher temperature buys you a lot more value heat that you can get, that you can also store, and you can drive for example, a supercritical CO2 cycle, which has a much higher efficiency than what you get from a steam cycle. Another byproduct of running a cycle at higher temperature is you can use that heat for processes. And in Australia, you have a lot of mineral processing that needs to be done at temperatures well above 400, 500 degrees Celsius, which a common solar thermal plant would not be able to provide to you. This plant that we have been looking at more recently runs at a temperature of roughly 700 degrees Celsius on the power cycle. And with that 700 degrees Celsius, you can run the supercritical CO2 cycle, and you get much higher efficiencies of the overall plant. And you could use that heat at that temperature also for some mineral processing. So that's something that we're looking at as well. But let's focus at the moment on solar power, so on power generation for this, because that's the main focus of the Astri program right now. What we want to do is look at that blue curve. We want to drive down the cost of a solar thermal power plant. And one way to do that, I use an example here, is to reduce the cost of the components. So when you look at the heliostat field, for example, and you look at the cost of the mirrors installed in a field, today we're roughly, depending on who you ask, between the $200 and $300 per square meter. That's fully installed, fully commissioned field of mirrors. So if you want to lower the cost of electricity, this is a direct correlation only driving the cost down of the mirrors. So if you want to drive down the cost of the mirrors, you can extrapolate that curve, and you have to almost get to zero to hit a cost point in this vicinity where you want to get. So without changing the cycle to a high temperature, you would have to follow this curve, and you don't get where you need to go. So going to a high temperature cycle, we can move from the blue curve to the red curve, and that gets us in the vicinity of somewhere between 6 and 8 cents a kilowatt hour dispatchable power, dispatchable energy. And then it becomes attractive. So if we reach that point, which we believe with the technology we're working on we can do, then we should be able to get a solar thermal plant in the vicinity of an electricity price where it can make sense in the energy mix in Australia. So why do I say that? Because there have been recently some studies, and this is new. I know this hasn't been published yet, but it will be. There has been a study by Energia, and there has been a study by AEMO on, and I think there are a couple of others that have done studies on what could be the energy mix on the future if we get the cost to where we believe today we can get them. And this chart can be a little bit confusing because it has a lot on it, but I want to point out what to me was very interesting is the portion of CSP on this chart, which I think the colors are mixed up. Somehow this thing oh no, it's right here. So it's the gray one right here that is 0 today, because there is really no power generation from solar thermal today. But if we get that cost curve down, this was a pure analysis, economic evaluation of the energy market, the NEM, of what technologies would be picked up based on their capability, based on their cost, and the location where you need the energy. And this study, amongst others, showed that there is a small role for solar thermal that it will be picked up purely on economic evaluation. Okay? So that gave me a good feel. It's like, okay, so if we're successful with getting the cost down, then there should be, in the forecast at least, a situation in the NEM where solar thermal will be picked up by the industry as a solution for power generation. So that was a first test. The question is, will it be? So if it can be, we also have to make sure that it will be, and those are two different things. The fact that a model shows that it can be picked up doesn't mean naturally it will be picked up. So what do you have to do to get there? So first you have to ask yourself, where will it be picked up? What is the situation, or what are the locations where it's actually going to be needed and where it makes economical sense in the Australian grid? So this is part of that study that was done, and it looked at the NEM and the different locations of the towns. And what is actually interesting is that the first locations that economically make the most sense for this to be picked up is the fringe of grid. So it's not near Sydney or near Melbourne. It's in the places that are not completely remote, so they're not off-grid, but they're on the edges of the grid, on the fringe of the grid. And I was explained, this was new to me, that the reason for that is that it's very costly today to support the power lines to the fringe of grid. And that comes into the economic evaluation as well. It's not just comparing CSP with a coal-fired power plant, because you wouldn't put a coal-fired power plant in those locations. But comparing what you have today and what you have to provide to make sure that people that live there and people that have industries on the fringe of grid have electricity at a price that is actually okay for them, you have to ask yourself, what does it cost today to provide that electricity to the fringe of grid? And something that I also learned is that today there are subsidies from the government to make sure that some towns on the fringe of grid don't have an outrageously high energy price. So comparing the actual energy price today, or what they're paying, with a plant that you would put in there is also dangerous, because the energy price is subsidized. So what you also have to think about is how can we offset the cost to the government of providing that energy at a certain price today. So you have to put that into your economic evaluation. And when you do that, as the model shows, it actually turns out that over the next few years, there is economically a need for something like solar thermal, also PV, by the way, in the areas of the fringe of grid that will offset the cost of operating the grid to run out there. So that's something that wasn't originally on my horizon when I looked at solar thermal. I was comparing it directly with power plants today. But it's something that you really have to consider when you look at the overall solution of a power generation in Australia. So it's not just the power generation, it's also the delivery of the power. And there's another aspect that did not go in here. It's also the stability of the grid you have to worry about. So you want to make sure that the generation you provide gives you a stable grid. Stable grid means you don't have too much frequency variation, and you don't have too much voltage variation either. And that's something where solar thermal, being a synchronous generation, can help the grid being more stable as well. So given the fact that PV is so far down in price or in cost, I was asked by some people if PV is really the competition for solar thermal. And in my opinion, it actually isn't. In my opinion, the more PV you have on the grid and the more wind you have on the grid, the more power generation you have through a converter-driven power generation, the more there is a need for synchronous power generation. Now you could argue, let's just build more power plant and you have more synchronous generation. But you could also argue, CSP is giving you that same synchronous power generation that you could have in the location where you need it, and you get actually more stability. So we did a quick analysis what that means. If you have PV power plants without storage, and you have CSP, how much more PV power can you feed into the grid if you have CSP to go with it? And this is just an indicative curve that shows you that actually having CSP with flexibility, because remember, the CSP plant is fully dispatchable. That doesn't mean it provides you base load and it's fixed. It really means that you can choose how to run it, because it does have more flexibility than you would get from a large plant. So having that flexibility of very quickly adjusting the power generation from a CSP plant allows you to actually put more PV in the same location. So it's not a competition. It really should be a hand-in-hand working. More PV means more need for CSP as well. So that's how I like to look at it, that it can actually help getting more, overall, more solar power onto the grid. So that's why I like to have this slide saying, I almost put on there CSP and PV are friends. Well, I was a little bit more careful, said they're definitely not competitors. Okay, so that's the way I like to look at it. Is I mentioned earlier I've worked on PV plants and wind plants for a long time, and the one critique that has been given in Europe is also that, and I'm sure you've heard the same in Australia, we're making the grid weaker and weaker because we're putting more frequency converter fed power generation onto the grid. Well, there's one solution to it. You give somebody central control over all the power converters, because then you can create whatever frequency and voltage you want. I don't think that's going to happen, because I think that central control doesn't work in this setup, so it'll always be a dispersed control or distributed control. In that case, it actually helps to have more synchronous generation locally in the places where you actually need it, and that provides you inertia on the grid automatically because it's running through a synchronous generator. So that's why I like to look at it as they are really friends. And I'm not just saying that because I'm talking to a group of PV experts, but I really believe that to be true. So coming back to what are the advantages of solar thermal for Australia? So I sat down last night and asked myself, so how much did I learn in the last 2 months about Australia? And where can I see solar thermal really helping the Australian energy mix? There are a couple of things that are obvious, but some of them may not be that obvious. The solar thermal, because of the way the plant operates, it has a very low-cost integrated storage option, much lower than on a per kilowatt hour basis than lithium-ion batteries, for example, because you need it to operate the plant anyway. So naturally you have storage with the plant. So you just increase it a little bit to have a 6-hour, 10-hour storage as you see fit. That's one big advantage. The other one is, compared to PV and wind, it is fully dispatchable. So it provides you, from solar energy, a fully dispatchable power generation. A third one, I mentioned this already, is it provides you synchronous power generation, and not only at a very large centralized power plant, but in local pockets. And I didn't mention that the size of power plants on these fringe of grid areas that we looked at is typically 20 to 30 megawatts. So it's not hundreds of megawatts, but it's a smaller size. So it provides you grid stability. This is something that it's a little shaky, but I'd like to look at it in comparison with PV. When you look at where are the components for PV manufactured today? Most of them are manufactured in China or other places outside of Australia. There are, as far as I know, not many converter companies in Australia. There are not many PV panel companies in Australia. So the local content of making more PV plants it's not zero for PV, but it's certainly limited. When you look at solar thermal, it's a new industry. But it is a new industry that's relying on more conventional components. You need a turbine, an expander, you need heat exchangers, you need a gearbox, you need vessels, you need piping, you need mirrors, you need structures for mirrors, you need control system. So it can have a lot more local content because there's an industry in Australia that is very adjacent to it. Some of them are from the car industry that can actually shift and make components for solar thermal. So it does, in my opinion, have more chance of having a local content for Australia. And it does have the potential for using the high temperature in process heat directly. It's much more efficient to use the heat for processes directly when you get it from the sun, rather than having the sun create electricity and then use electricity to drive heaters. So the efficiency is much higher. The cost of heat is much lower when you use it directly from a solar thermal plant. And there is an applicability for combined heat and power. Now I do understand that in most places in Australia it's quite warm. Now I live in Melbourne, I can tell you it's not always warm there. And combined heat and power is also an opportunity you get with a solar thermal plant. So that applicability, we haven't really looked into detail into that yet, but it's an option that comes with the plant itself. So those are the advantages for solar thermal. So are there only advantages? Well, there are some challenges that I see. The first two challenges that I put on the slide are perceptions. They're not really there. I talked to some people at ARENA and some people outside ARENA, and some of them mentioned to me, yeah, but it's such a complex plant. It's a lot more complex than a PV plant. And I said that is true. But I don't like to compare it with a PV plant. I like to compare it with a coal plant because it's not more complex than a coal plant. In fact, it's less complex than a coal power plant. And we've been building them for decades. So the complexity of it should not tell us, let's not do it. The other thing was its high cost. And I have to be honest, before I came to this job as being the director for Astri, I was a skeptic of solar thermal because I had in my head solar thermal cost somewhere in the 30 cents per kilowatt hour. And when you talk to most people outside of solar thermal, that's still what people have in their heads. Well, it has been demonstrated to be in the 12 to 14 cents per kilowatt hour already. And I think with getting more technology in there, we'll get it in the 6 to 8 cents per kilowatt hour. I don't think it'll ever be 2, honestly, but I don't think it needs to be. I think in the range of 6 to 8 cents a kilowatt hour, it certainly makes sense to put it as part of the mix. And I hope I was able to tell you that today, or show you that there is a chance for it to be there. And I want to be honest, I want to make sure that solar thermal is a solution that can have a play. And if we find out that it cannot, then we shouldn't invest in it. We should really be thinking of what is the best solution for a country like Australia, and is solar thermal a part of it? And that's something that's the role of Astri today, is figuring out, is there a role for solar thermal in Australia? And if there is, what is it? How can it play? So the next challenge I put on there is, it doesn't make sense for solar thermal to be installed on your roof. I would not put it on my roof. It doesn't make sense to run a solar thermal plant that's a few kilowatts large. So you do need some sizable plant for the levelized cost of electricity to be at an acceptable point. Where is that point? Our analysis has shown that in the 20 to 30 megawatt range, it starts actually making economical sense. If you go way below that, it probably doesn't. But you don't need to go to hundreds of megawatts. You don't need to go to gigawatts size of plant. So we need to make sure that we can drive the cost down in a size of the 20 to 30 megawatt range. And that's still a challenge that needs to be done. And there is a low amount of install base. In fact, you can count the installations on Earth. There are actually websites that do that, where you can have a spreadsheet of all the installation of all the solar thermal plants. And every single plant that's been built is a one-off. So it's not like, and this is what you mentioned earlier when we had coffee, it's not like PV where you have millions of them built already and they're all the same. Well, at least it's a product, and it has a very clear definition. When you look at the different solar thermal power plants in the world, they're all different. There's not a single set of two that are exactly the same. So every time we build solar thermal power plants today, it's a one-off thing. And that makes it difficult. But I think that will change because the installations that I see coming up are getting more and more. As the volume gets driven up, we will get to a point where there will be installations of either a modular plant where you have same modules over and over. And I know Vast Solar is one company that's looking at that, having a modular setup. And that will help driving the install base up and having more reference plants. So what we need to do, if we want to be successful in Australia, it's not enough to have a PowerPoint presentation like I do that shows you it can be done. We did the analysis, believe me. What we have to have is a demonstration of the right technology that we can show to the industry that it actually works. So what Astri has done in the last 4 years, Astri has been in existence since 2012, but really running since 2013. So it's been running for four and a half years. And what Astri did initially in the first 4 to 5 years of the project was to look at what technologies are needed to get that cost curve down. And what you see here is some cost comparison between different organizations, including the ones from Astri, that has driven down the cost through technology development. So we have come down the cost curve quite a bit, and we want to continue that for sure going forward. Astri is now planned to run until 2021 or 2022 to come down in that cost curve. But that's only part of it. Running that cost down with demonstration of little technologies in the lab is only part of what you need to do. We need to increase the technology readiness level of each of those components. What do I mean by that? Is coming from a company rather than from a research organization. If you're running a research group within a company and you develop something that is small in a lab and you go to a business unit and say, here, I showed that it works for you, now make a product out of it, you get laughed out of the room. That doesn't work. You have to make sure that you can demonstrate at a reasonable size in a reasonable environment that the technology actually is cost effective. So that's something that Astri has to do. We have to make sure that at a technology readiness level of somewhere in the 6s range, we can show that these high temperature technologies really work. So that is the first thing of what Astri needs to go and do now. We need to have a facility, a test facility, where we can show that the components are not only great, but they can also work together. And that's something that often gets forgotten, that you also have to show that you can operate them together, and that it's like a sports team. If you get the best, what's your favorite sport? Footy or rugby? If you get the best rugby players in the world and you throw them together into a team, will they make the best team? Probably not. So we have the same problem here. So we have the best components that were developed in Astri and other places, and we know they can get the cost curve down, but do they actually work together? And once they work together, will they create that high efficient, low cost system? That's something that has not been demonstrated. So we have to demonstrate that. And we have to demonstrate it not at a multi-megawatt level, but at least at a few hundred kilowatts level. It's not enough to have it in the lab sitting there and then show, oh, look, this little thing works. It has to be something that people can come and see and say, yes, this is representative of what a plant would do, what a plant would look like. Then we can go into industry and say, this is a right setup that you can take, and you can build that. But what we also need to do, and we have done this in the past 4 years, but we need to continue, if we want to have solar thermal play a role in Australia, we need to have capability in Australia to do that. So Astri's role in the past 4 years has been to develop PhDs, postdocs, and also people at CSIRO that create this capability and be known in the world to have capability in solar thermal. And it has been quite successful, but we need to do more of that. If we want to have an industrial uptake on something new like solar thermal, we have to have experts here that can help us do that. So building capability is still in the list of things that we have to do. The next one is international solar thermal community. So it's actually interesting. The solar thermal community worldwide, I learned now, they all know each other. So it's small enough that they know each other quite well. If we want to be successful in Australia with solar thermal, it's not enough to just sit in our own continent and do it. We have to connect with the rest of the world, and that's Astri's role as well. We are one of the, I think it's similar to ACAP. So we are Australia's representative for solar thermal in the international community. And that's something that is a very important role for Astri as well, because we're not the only country that's developing this. There's the US, there's Europe, and now there's China coming in developing solar thermal. And if we do it together, I think we're going to be successful in getting there. We also, since commercializing it and getting it into a state where it will actually get uptake, we need to start engaging with industry. And what is the industry that is actually interested in solar thermal? I mentioned earlier already, it's not just the energy industry. It has to be the industry that's going to make these parts as well. So we have to engage with OEMs. We have to engage with the end customer. We have to engage with the energy providers in Australia, the NGLs. I don't know them all yet, I'm learning them. But we have to start engaging with them so that we're solving the right problems. If we have this beautiful system sitting there and find out, but that's not solving the problems of the people that are actually going to be using it, then we're not going to have success. So we need to start engaging with the industry as well so that we can commercialize it. ARENA, who's funding the Astri Institute, has also asked us to become the advising body to ARENA on future projects. So ARENA would like to fund solar thermal projects in the future, but they need some advice in what are the right projects, what are the right size projects, where should they be located, what should they be funding, and what should they not be funding. So they'll be looking to Astri in the solar thermal world to get advice on what are the next projects that ARENA should be funding. And last but not least, we should also think of ourselves as being the advising body to the industry on commercializing solar thermal, being the pool of experts that the industry can come to and solve problems that will arise as you commercialize the solar thermal plants in Australia. So there's a lot to do. I'm new to Astri. For the last 2 months, it's been a whirlwind already, learning about the technology, learning about the environment, learning about Australia. My take on it right now is there is a big chance of it. Can I say that it will definitely be the solution? No, I can't. I don't know yet what it will be, but I want to make sure that we do everything we can to get us to a point where we can decide that, to get us to a point where we know it will have a place or it won't. And if it doesn't have a place, then quite frankly, we shouldn't waste money on trying to develop it if there is no road to get there. I don't think we'll find that. I think we will find that there is quite well a path, but we don't know exactly what that path is and what it should be. So we need to identify what are the right applications for it, at what price point are they right, what are the technology challenges to get us there, and then demonstrate that it can be done. Sounds like a simple task, right? Well, we have a few years to do it, and it's an exciting road, and so I'm quite happy to be in this role, and I'm quite happy to help where I can. I guess you realized already by what I'm presenting, I'm not the expert on solar thermal. That's not why I was hired. The experts are in the team. There are several experts in the team. The experts are in the community, and I will need to draw on all the experts to help us find the right solution, and that's really how I see my role. So that's where we are. Astri is an institute that is actually consisting of several different partners. So it's CSIRO is one of the main partners, but so is the Australian, or it's ANU, it's Flinders University, it's QUT, University of Adelaide, University of South Australia, and the University of Queensland. We do have some US collaborators that we're still working with because the US is also, through the Department of Energy, driving a lot of solar thermal programs today. One of them, for example, is the supercritical CO2 power cycle. So we don't have to do a lot of it ourselves. We will do a little bit, but we will collaborate with other institutes in the world that are developing technology already, so that we don't have to do it all ourselves. And we'll provide some of what we find to them as well. So the last slide I have is an acknowledgement. Yes, we are completely funded by ARENA at the moment. That may change in the future. We may be able, as we get industry to work with us, we may be able to also attract funding from other bodies. But at the moment, it is fully funded by ARENA. And with that, I want to thank you. I actually didn't check the time, so I don't know exactly how I was going on time. Yeah, thank you. But I think we have time for questions. Yes?
Thanks for the talk. Very interesting. So in just thinking about moving to the high temperature system, it sort of, in my mind, it means that you have to change every single component in the plant from what's currently out there. And that adds a lot of risk. Do you think it's a good idea to just do it all at once, or to just do one component at a time? You know, like Fast Solar has sodium as the working fluid, but they're still using a low temperature power cycle, right? Which approach do you think is best?
So I think the technology on the components individually has already been done. So we've already seen the sodium loop with Vast Solar. I was talking with them. In fact, I'm going to the Vast Solar plant next week. So we've seen that can be done. The challenge that we have to do is actually the integration of it. That's the biggest challenge we have today, is the integration of all the high temperature parts. And so that's why I said we have to do it together now. It's not enough anymore to just keep continuing on testing the individual components.
But I don't think these components have been tested at scale, right? Like supercritical CO2 cycles haven't been 100 megawatt scale cycles yet.
Yeah, so the program in the US is doing the supercritical on a large scale, so that we don't have to do that. But we are working with them. Well, there is a program in the US, it's called the STEP program, that is actually developing a 10 megawatt supercritical CO2 turbine right now. They'll scale that up to 100. So we're working with them, but we don't do it ourselves. We're developing a smaller one that we can use for integrating it into our system. Because what also hasn't been done, nobody has integrated a supercritical CO2 with a receiver. and shown that it actually works on the sun. So I see the most critical part of Astri going forward is to show that I don't think there's such a word as integratability, but the integration and how it works together. In my opinion, that is the most challenging part that we need to address. Yeah. But you're right, it would be easier to just develop the components, but the danger is to go with the components already to develop them to scale without knowing if they actually work together may lead you on the wrong path. Okay, so if for example, if you figure out that sodium with a sodium heat transfer fluid with a supercritical CO2 cycles has some inherent problems that it doesn't really work together, then you waste a lot of time and money on developing large-scale components if they don't work together. So we have to do both in parallel. And the focus of Astri is going to be developing that integration demonstration in the future, and at least on some of the components like storage, we're still focusing on the actual component as well. So storage and receiver is something where we continue focusing on the component and larger scale of the component. And the rest, like the heliostats, for example, they're not going to change. We changed some of the heliostats, but they're not going to be implicated by the higher temperature. They're not going to see that. But on the receiver and on the storage, there the higher temperature clearly is a challenge. And there we're going to continue to focus on the components also on a larger scale. In fact, we want to integrate the storage with the receiver as a standalone, smaller integration unit before we throw that all into an entire system. So there will be some subsystem integration before we put it into a larger system. But the ultimate goal has to be showing the integrated operability of the components with each other. If we don't get there, then really we haven't succeeded. We have to show that it also works together. Yeah. Does that answer your question?
Yeah, I mean, I just think of Vast Solar, and they you know, I talk to them a lot. I have a project with them, and they just want to do one risky thing, and keep the rest all very, you know. So if they want to get financing, they can say this is proven, this is proven, this is proven, and we're just going to add the sodium loop, and that's the only thing that's new. And then they can get, you know, the bank to give them money and fund and investors and stuff to build the plant. But if you try to redesign everything all from scratch, that's a lot of risk.
Yeah, but I don't think we're redesigning everything. So I'm actually glad that Vast Solar has tested a sodium loop, and we're going to work with them. I talked to Greg Wood a couple of weeks ago, and as I said, I'm going to meet with them again next week, and we want to actually do some integration testing at their site. So before we test a sodium loop in our integrated system, I'd like to use what they already have and do a first integration at their site to make sure that works. And that will de-risk it to some level. And then we have to come back and have it all together and demonstrate that it works. And also, you have to be able to come to industry and say, we have a solution that can be cost effective and it can work, and here is an entire system. Look at it. That's how it works. And that's something you have to have. And if you don't have that, it's very hard to convince. If I was an energy company that wants to invest in a new plant and you'd show me a PowerPoint and some components that work together, I would not invest in it. Because that's something that would not show me that it actually works. But if you have something that works together, then you have ticked off the box that to test the components at a sizable range at a place like Vast Solar, for example. And the next tick off the box is, and you demonstrated, at least on a smaller scale, that you can actually operate them and they actually work together. And that's what Astri has to do. So you do have to do both. Okay, I'll start here and then over there.
Yeah. Could you give an update on the status of the Port Augusta solar thermal plant? Because that's been announced for years and I don't know where it's up to.
So I actually don't know. I know it's being discussed. I met with the ARENA board a few weeks ago, and to my knowledge, it has not been decided yet how to go forward or if to go forward. So that's something that's still in discussion. But to be quite honest, Astri is not involved in the Port Augusta plant at all. So it's not part of Astri. And I think there has been some involvement in the past about consulting with them, but we're not involved in the Port Augusta plant. So I'm sorry, but I don't have an answer for it. Yeah.
Yeah.
Thanks. So you mentioned that you see the competitor not as, say, PV, but rather, say, other synchronous generators. Do you see that this technology has a particular advantage compared to, say, a coal synchronous generator in terms of its dispatchability? For example, is it faster to respond to changes in demand?
Yeah. So since the plant is smaller than a coal-fired power plant, it responds much faster to a power output change than a large turbine would. So a coal-fired power plant is several hundred megawatts, and it's just by sheer physics, it takes you minutes to change the load on that type of a turbine, whereas you can change in seconds on a smaller turbine. So that in itself already makes the response time of it shorter. By how much shorter, I actually don't know. I haven't done the analysis, but it does have an advantage over a coal plant. But I didn't really compare it to a coal plant because I think the big advantage over a coal plant should be that it should be cheaper than a coal-fired power plant. Plus, when you think of rather than thinking of competing with existing coal-fired power plant, you have to think of competing with new coal-fired power plants that will be built. There's also this question about financing power plants. So when you think about investors that are going to invest in new power plants, it's much more risky to put down a lot of money for a large power plant where at similar costs, you could get smaller chunks of it because you're actually de-risking your investment when you do that. So that's how I like to think of the advantage of a smaller power plant driven by solar. It's also cleaner than coal over a coal-fired power plant. But just intuitively, it should have a faster response time than a large coal-fired power plant because of the physics that come with it. But to be really honest, I haven't done the analysis. It's just pure intuitive. Yeah. Yeah.
I don't know if we can go to slide 12, but you had that interesting energy mix that showed, that one with the, and it seems that there's a huge increase in natural gas, which I assume means building new natural gas plants. So my question sort of follows on from what we've just been discussing. Is there an opportunity for CSP to provide a solar component to that expansion? Because, naively, you'd assume you're making those capital investments. It would be a great opportunity to fuse the two. The Kramer Junction plant, which was built in the 1980s, is co-fired. It has solar and gas at night.
Yeah, that's a very good comment, and that's actually a very true comment as well. At the study, that wasn't considered. At the study, it only considered purely on economics. You have a need for new power plants. Which one would you build? And in some cases, but they didn't look at hybrids. They only looked at would you build a natural gas plant, or would you build a PV, or would you build a CSP, or would you build a coal-fired power plant? And that's really how they did the study. Now, I didn't do the study. They did. But it's a very valid point. If you consider hybrid plants, how will that change? It's a good question. I don't know the answer to that, but I would like to see that it will actually increase the amount of solar thermal in the mix. I would like to be able to say it, but I haven't done the study. So again, intuitively, I could see that would happen. But this is actually, for me, the most conservative look at, is there a role for CSP? And I was very happy to see that there is, even in this scenario, there could be economically a role for solar thermal in it. But you're perfectly right. If we are successful and if we're increasing on looking at hybrid plants, or even if we're considering not only the electricity demand, but also heat, how will this change the need for solar thermal? It can only go up from there. It will not go down from there. That's exactly where I am with you as well. And that's something that we do need to look at. Yeah, thank you.
Yeah, I'm just commenting on the chart. It seems to be missing a couple of labels because the natural gas is probably the lower one, and the top one is not labeled.
Yeah, that probably, because I just copied it out of a report yesterday, and I may have expanded it too much, so it may have dropped off. Yeah, I'll go back and fix that. Thank you.
So I think that the natural gas is the third from the bottom.
The natural gas is this one. That's a natural gas. Because it actually goes, I'm pretty sure that's an...
It goes from the bottom up, but the top one's on this.
The top one is rooftop solar and energy efficiency.
Oh, okay.
I've seen...
you've seen this chart?
They've, or something very similar from AEMO. They're actually predicting a flat demand for energy, around 200 terawatt hours. The orange slice is the bit that the market doesn't see. So it's energy efficiency and rooftop solar.
Okay. That could be.
Okay,
but that's a very good point, because I just put that together. And okay.
Yeah, the solar generation figures just looked a little bit low, so
Yeah, that's because that big chunk is solar as well.
Yeah, and I think you're right. Yeah, thank you.
Rooftop solar.
Yeah.
I'm going to have lunch with you, so I'll ask my questions then. And
Okay.
the people who are not going to have lunch, ask.
So this might be pie in the sky, but is there any technology to use it as a storage element or like a load element for the grid? So I'm thinking South Australia in the Port Augusta example, which is a grid dominated by wind at night. Could you potentially have heating elements to store any excess energy from the grid when it's cheap as heat, rather than just using the solar element? Is that being looked into at all?
The question is pie in the sky, because I'd actually, the answer I would give right now is possibly yes, depending on how we're going to drive the cost of storage down. Because we're looking at different types of storage at the moment. The best way that we currently think of, because of the narrow temperature range you get with it, is phase change material. And if we can get that to a cost-effective point where you could use it as storage alone, then yes. But what you could also do is, if you're building a CST plant anyway, somewhere near that area, and you make the storage large enough that it can also take from electricity you create otherwise and put it in the storage as well. That's right. If you already have it anyway, why not also use it as storage for PV generated power as well? I haven't thought of that. That's hasn't occurred to me that would be an option. In my experience, usually when you generate electricity, you should use it if you can. But if you cannot use it, you have to find a storage to put it somewhere. If you have the storage already, by all means use it. It's more cost effective than installing an additional storage.
Yeah, I'm thinking of South Australia being the prime example where it's forecasted in the near future that there'll be days where there'll be so much excess electricity and they're interconnected constrained, and they don't have effectively enough storage in their state to essentially put it anywhere. So it's just the...
Yeah. Now you lose efficiency if you use that electricity to then put it back into the heat generation. So the way that we have looked at the plant, there is no component in there that allows you to feed electricity back and then heat up the thermal storage, but you could actually do that. Other ways to think about it is create fuels from your electricity that you have, right? And then use it, because I mentioned earlier that we shouldn't only look at the electricity grid in isolation. We should really look at the overall energy need. But I only mentioned electricity and heat. There's also transportation. And I think almost 1/3 of the energy need in Australia, because it's so big, is transportation needs. So how do you solve that? And then it makes the story much more complicated, but it is something that needs to eventually be looked at, is how do you incorporate the need for fuel in this overall mix? And for this talk, I actually left that out because it would just overcomplicate the picture. But to be complete, you actually have to look at the entire ecosystem of energy need, which is electricity, heat, and transportation. And how do you find solutions to store the energy that you get, to use it in place as you need it, to distribute it? So it's a very complex thing. And what I would like to see, this is my dream, I would like to see a model that combines it all, where you can actually test how things come into play and what is the optimal solution. I don't know if it's doable. My background is computational fluid dynamics, so I used to build large models, and I think solving the problem of modeling turbulence is at least not easier than solving the problem of having a model of energy. But I haven't seen it yet. I haven't seen it anywhere, not only in Australia. I haven't seen this in the US or in Europe either. A complete model of the overall energy infrastructure and need that you have. That is something that I would like to see universities tackle, actually. Can you build a model like that will accurately allow you to throw different solutions in and see how you can combine them? That would help you also see, can you have storage here? Can you have fuel generation here? What is that ideal mix? I know it's not easy to do, but it's a dream of mine that somebody comes up with that type of a model. Okay. If there are no more questions, then thank you again.